Hello all. Today we discuss about steady state error time domain analysis. First of all, steady state error is a parameter of accuracy of a control system. Therefore, steady state error should be minimum as far as possible for a good design or for a good to increase the sustainability of the circuit. Okay, so first of all, the steady state performance of a control system is assessed by the magnitude of the steady state error possessed by the system, and the system input specify as either step or ramp or parabolic. There are various kind of system inputs are available, like a step function, ramp function, and parabolic function also. Now, for an open loop system, for the classification of the open loop transfer function is basically in a typical form. We expressed in a for a classical system classification of a system. Sorry, so only there is only represent GS and HS is a typical form approach is known as is S into T1 plus 1 into S T2 and divided by S to the power n is the order of the pole 1 plus S T1 dash plus 1 plus S T2 dash. So here K is the known as open loop gain or forward path gain. It's an open loop gain or forward path gain. Okay, and next one, here the location is minus 1 by T1 and minus 1 by T2, minus 1 by T2. So minus 1 by T2 are the location of the zeros location where the system gain equal to 0, and minus of 1 by T1 dash and minus of 1 by T2 dash is the system poles location while the system gain equal to infinity. Okay, we already know that. And here n is the number of poles at origin, because there is no coefficient with this s to the power n means the pole at 0. Now the number of poles at the origin defined by the open loop transfer function is the basis of the classification of a control system. Say if this n equal to 0, then this is known as type 0 system. Okay, if it is 1, then it is known as type 1 system, and if it is 2, then it is known as type 2 system, and so on, and then for type n system. Okay, now consider for a feedback control system, one loop for a feedback control system. Here one comparator between the input signal and the feedback signal RS, and here we generated our error signal ES, and here the block is present is known as open loop gain GS or forward path gain GS. Here the output response CS, and here present one feedback path gain known as HS, here connected to this feedback path. So there is a positive and there is a negative monetary phase shift. So now we already know that from this block diagram the expression of ES by RS is basically 1 plus GS into HS. In the previous video you will see that. Now what is the value of ES? ES is basically RS divided by 1 plus GS into HS. Okay. Now next, applying the final value theorem from the Laplace transform, we already know that the steady state error is basically limit S tends to 0 S into ES. That means limit S tends to 0, here S into RS, putting this value divided by putting this value of ES here, GS into HS. Okay, so now this is our final equation. So now this is known as, noted that the steady state error represented by the ESS and for the closed loop control system. Okay, and now here we measure some parameters are known as static error coefficient. Okay, static error coefficient as it with the input as determined. So number one, first static positional error coefficient. So first we study static positional error coefficient. Okay, now these are study. Static positional error coefficient is defined by Kp positional, that's say P is assigned with the step input signal applied to the closed loop control system, and determined is follows. So now what is the steady state error? ESS, you already know that final value theorem, S tends to 0, S into RS divided by 1 plus GS into HS. Okay, so now our input is step. So what is the Laplace transform of input step signal 1 by S? We already know that. So now we put this value here, so now limit S tends to 0. So now this is 1 divided by 1 plus GS into HS. So now modification this formula, 1 divided by 1 plus limit S tends to 0 GS into HS. Okay, right? So now this is the system transfer function. This is a steady state error function. Now here the parameter is Kp, which is equals to limit tends to 0 GS into HS. So now this is known as the positional error coefficient. This is very important. And now putting this value here, what is our steady state formula? The steady state formula is 1 divided by 1 plus Kp. Yes, right. Okay. Okay, now second one is we define static velocity error coefficient. Now we define static velocity error coefficient. Okay, now for this we consider here input is a ramp signal. So basically this input signal is basically ramp. And what is the Laplace transform it? Because ramp function is basically t, that means 1 by s square. So now what is our steady state formula? Limit s tends to 0 RS divided by 1 plus GS into HS. Okay, clear? Now we put the value here. So now here limit s tends to 0 here on S here. Yes, right. Here on S here is present here. So now here the formula is limit s tends to 0. Here R is equal to 1 by S square. So that's why this is S into GS into HS. Right. So now our formula is as s tends to 0, this part equal to 0. So it's only present in here, that is S GS into HS. So now velocity position error coefficient is defined by Kv. This Kv is basically limit equals to limit s tends to 0 S into GS into HS. And finally the steady state error, from this expression we put here 1 divided by is basically 1 divided by 1 divided by Kv only, just of okay, because this is the value of Kv. Okay, now next third one is very important, also important. Now static acceleration error coefficient. Static acceleration error coefficient. This is denoted by Kf. Now how to calculate it? Again, the steady state error is defined by limit s tends to 0 S into RS divided by 1 plus GS into HS. Okay, now next here input equal to parabolic, so therefore RT equals to basically t square. So what is the Laplace transform here? 1 divided by s cube. Basically these are 2 factorial by s cube. Just consider the magnitude, just no constant parameter are considered for simplicity the calculations. Okay, now limit s tends to 0, here s divided by s cube into 1 plus GS into HS. So now finally we see that this is 1 divided by limit s tends to 0 s square GS into HS, and this value is equals to known as Kf. So basically steady state error is basically 1 divided by Ka. This is also known as acceleration K or Kf, any one. So either this is Kf or K, any one. Okay, so or Aka here or Kf, that is ESS is basically 1 divided by K or Kf, etc. Okay, now this is a general discussion about the 3 error constants three error, steady state error, and their constants are coefficient. And now we discuss about type of transfer function and steady state error. This is very important. Okay, so now our discussion point is type of transfer function. This is the short form transfer function, and steady state short form steady state error. Okay, so now this is our topic. So now first we discuss about type 0 system with unit step input. Okay, now study this. Now what is the function of gs into hs? The general expression is, we know that already, k into 1 plus st1 plus 1 plus st2, we already know that, divided by 1 plus st1 dash 1 plus st2 dash, and so on. Now kp, you already know that kp is basically limit s tends to 0 gs into hs. Okay, so now putting this value here, putting this limit value here, so now we're getting the value, this kp is basically k, because this function is already from here, the value is only k. Okay, because if we put here gs into hs, then only k value is obtained from here. So now if we putting this value in the steady state error, that is 1 divided by 1 plus kp, so instead of kp we put here 1 divided by 1 plus k. This is a gain of the system. Okay, so now we discuss about, focus on that type 0 with unit step input. Now we discuss about again type 0 with ramp input. Okay, now again for the transfer function gs into hs. Okay, so for the transfer function gs into hs, again we write this k 1 plus s of t1 1 plus s of t2 dot dot divided by 1 plus s t1 dash 1 plus s t2 dash, and so on. Now what is the formula of kb? Velocity acceleration coefficient, velocity error coefficient, sorry, limit s tends to 0 s into gs into hs. Okay, now what are the value coming from here? This is equal to 0. If we put here, now ess is basically 1 by kv, that is equal to infinity. Okay, now this is the value of steady state error when type 0 response with unit ramp input. Okay, please follow this carefully. Now next one is number 3, type 0 system with, yes, right, parabolic input. Parabolic, this is very important, parabolic input. So now for parabolic input, 1 by s cube, already know that. So for gs into hs, therefore we write here our the main parameter ka is basically limit s tends to 0 for the final value theorem. We see that this is s squared gs into hs, and if we put gs into hs here, student, please do it yourself. This from gs from the same value gs and hs put here, and ultimately the k value equal to 0. Therefore steady state error again 1 by ka, that is equal to infinity. But type 0 system, we see that. Now there are another system known as type 1 system. Now we discuss about type 1 system. Okay, with unit step, again for unit step. Okay, one change is coming here. For a type 1 system, we already know that the one pole is exist. That means here the only change is gs into hs, that is equal to a into 1 plus st1 1 plus st2 divided by 1 plus st1 dash plus 1 plus st2 dash, but here one pole is exist. See that in a normal type 0 there is a no pole, but here one pole. Now it's the same calculation for kp, kv and ka also. Okay, I just write here, student, all student, please do it yourself. Here first of all, when kp value, the value of kp here basically that's equal to infinity. Okay, first of all, that means k equal to infinity. So therefore steady state error for this system equal to 0. Now for the kv, if we come here kv equals to k, okay, the velocity error coefficient, and ess equals to basically 1 by k. Okay, for k here, k for a type 1 system, the k is becomes 0. Okay, and ess equals to 1 by k, that is equal to infinity. Please do it yourself. Okay, and similarly for the type 2 system, the change here for the type 2 system, the change of the transfer function is again gs into hs divided by equal to 1 k into s t1 1 plus s t2 divided by 1 plus s t1 dash 1 plus s t2 dash, and so on. And here s square is coming present because they are two pole type 2 system, only two polar exist in the origin. Now same for calculation, first kpk, then ess, then kv for ess, then ka, and evaluate the ess. Okay, so this is a overall discussion and thorough discussion of about the type 0 and different types of error coefficient generated in a different types of order of control system. Okay, that's a very important parameter to measure the performance of the system, to measure the. Okay, next we talk about the generalized error coefficient. These are generalized error coefficient are the most important part, because we expressed the generalized error coefficient is a coefficient, generalized error coefficient. The steady state error determined by using the static error coefficient, as we mentioned in the previous. So it does not give any indication as how it varies with the time, and is calculated for a step ramp and parabolic inputs only. So generalized error coefficient is to describe in the below is the steady state error performance of a feedback control system to any arbitrary input function. So that's why it is very, very important. Otherwise we will study separately unit step ramp, like in the previous slide we discussed about that. So it is very time consuming, and also the error performance and indication in terms of time and final steady state error is determined at t equals to infinity. So now first of all, starting our mathematics. So what is the error response? So what is a first of all error signal? This es by rs equals to 1 divided by gs into hs, first coming out here. Okay, so now we consider this function as a series known as Maclaurin series. This es by rs, okay, is basically considered as a Maclaurin series k0 into k1s. Why this Maclaurin series are considered? The spelling is Maclaurin, M-A-C-L-A-U-R-I-N, Maclaurin series. But why consider this series type formula? Because there is a system where is a pole exist. So that's why here only DC gain, there is a 1 pole, 2 pole, 3 pole and exist, and so on. So that's why you consider this type of expression. And now from this expression we know that es equals to this first of all one here k0s, okay, k0 into rs plus k1 s into r1 rs and k2 rs into s square, and so on. Okay, so this is our mathematical equation. So now if we convert the inverse Laplace transform et, you already know that this is k0 into rt. Okay, first this k1 into r dash t, that is first order derivative, then k2 equal to r double dash t, second order derivative, inverse Laplace transform after getting the inverse Laplace transform. So now in terms of steady state error, the following observation. So now for k0 is associated with step input. So now see that k0 is associated with step input. So now k0 equals to 1 divided by 1 plus kp. Okay, see that. Now k1 is associated with the ramp input, because here derivative from, this is a simple from, this is a double derivative from. So that's why here consider this is k1 equals to 1 by kv representation, and here k2 is associated with the parabolic input double dash. So that's why k2 equals to 1 by ka. Okay, you can just consider, and therefore the expression of et. Okay, now what is the expression of et? Et is basically 1 divided by 1 plus kp into rt, just putting the value here, 1 divided by kv into r dash t here, and 1 divided by k into r double dash t. Okay, and so on. Okay, so now we see that the error series given by this last expression is the last expression. All the poles and the transfer function lies in the LHS. Okay, and it's in the spline, and the generalized error series for a feedback control system is derived below. And first of all, the error of non-unity feedback control system, the error of a non-unity feedback control system is given by this expression ES divided by RS divided by 1 plus non-unity means this H is non-unity. That's why here we present H is in a typical form. It's non-unity feedback control system. So now just to consider here some function FES. Okay, this is equal to 1 plus GS into HS. Okay, so now we write here ES is basically others nothing, that is FES into RS, error feedback. Okay, FE is the error series of feedback control system. So now using convolution theorem, one theorem is applied here for the convolution theorem. From this we know that this is in a Laplace domain, and the convolution in a time domain is basically ET. E of t is basically Fe tau, the two dummy variable, into RT minus tau. That's a convolution. To convolute signal to each other, and that expression is also expressed by minus infinity to plus infinity Fe tau into RT minus tau d tau. This is an integral form of this error in time. Okay, so this is a very time consuming to measure this parameter. Okay, so one thing here mentioned that this RT minus t, basically this RT minus t, if we take the Taylor series form, then this is expressed RT minus tau r dash t plus tau square by 2 factorial r double dash t plus minus tau cube by 3 factorial r triple dash t, and so on. Okay, so this is our from the Taylor series expression we write here. And one thing, this Fe tau is basically expressed in a form t inverse Laplace of FES. Okay, so t into Laplace inverse of FES. Here r tau is an input function and tau is a time variable, as we already said that. So now if we putting this value here, that is ET, this value is putting here. So now first 0 to t, this Fe tau coming, and then in a bracket the Taylor series expansion of the RT minus t is r dash t plus tau square by 2 factorial r double dash t minus tau cube by 3 factorial r triple dash t, and so on, and last d tau. Okay, now taking limit of the above expression t tends to infinity, that is the final value theorem. So limit t tends to infinity, E of t, that is all expression are t limit t tends to infinite, that is integration 0 to t. Again we write this equation Fe tau, and in the bracket the same expression, this is d tau. Okay, the d tau. Now individual term in the right hand side, 0 to t RT is the first function RT, Fe tau d tau, then next 0 to infinity r dash t tau Fe tau d tau, and r double, and the another term is 0 to infinity just here, this is 0 to infinity also, sorry, 0 to infinity. The another term is r double dash t tau square by 2 factorial into Fe tau d tau, and so on. Okay, now consider this thing. Now this is a first parameter c0, second parameter c1, is a c2, and cn up to so what is the value of c0? So c0 equals to basically 0 to infinity tau square by 2 factorial, sorry, extremely sorry, f e tau to d tau. What is the c1? 0 to infinity tau f e tau d tau. What is the value of c3? Sorry, c2 first. 0 to infinity tau square by 2 factorial f e tau d tau. Just taking from this part. And the generalized expression is cn equals to, look here, 0 to infinity. What is the expression? Yes, right. Tau to the power n by n factorial. Yes, very good. Because it's the general expression f e tau d tau. So now this is our nth term of general expression of this error coefficient. So now we see that this ESS is basically C0 into, sorry, C0 into RT first of all, then C1 into R dash T, then C2 into R double dash T plus C3 into R triple dash T plus Cn by n factorial R to the power n T. Okay, so this is the general expression of the steady state error function. Okay, so now the expression in the above is the generalized error series of steady state error, and the coefficient C0 to Cn are termed as a generalized error coefficient. Okay, and now one thing is remaining. Now from the inverse Laplace and the Laplace definition, we already know that FES, error feedback, is basically 0 to infinity f e tau e to the power minus s tau d tau. Okay, tau is a dummy variable parameter expressed in a time domain. Okay, so now limit s tends to 0 FES, initial value theorem. So now limit s tends to, sorry, final value theorem, 0 to infinity f of e tau e to the power minus st d tau is equals to 0 to infinity, just simple the mathematics to follow the integration parameter. So this is equal to C0. Okay, now this is equal to 0 because we put here s tends to 0. So that's why this is a C0 parameter. Okay, so now from here see that C0 equals to basically limit s tends to 0. Yes, right, this is very important. So in a Laplacian form, in a Laplacian domain, any error function FES first we expressed and then put s tends to 0 and you get C0 equal to this value. Okay, and for similarly C1 is also getting from here limit s tends to 0, and this is the derivative term d of EFS by ds. So derivative first and then putting s tends to 0 and you're getting this value. So first of all derivative this by s, and what is the change in the integral, and after this putting s equal to 0. So first we take for this getting the CFN value, first for C1 value, first we take the derivative of this. So now here minus s is coming out, yes, minus 1 is coming out, and also tau is coming out, and putting s equal to 0 we get the C1 here, and C2 and up to C3 and Cn also. So therefore this is the process by which the generalized error coefficient and determine the generalized error coefficient value for any order system. Okay, for a time domain response also calculate.